Hey everyone, and welcome. Today we're tackling a LeetCode hard problem called minimum number of increments on subarrays to form a target array. That's a mouthful, but the core idea is actually quite beautiful and surprisingly simple once you see the trick. We'll break it down step by step. Alright, let's look at the problem statement. We're given a final destination, an array called target. Our starting point is an array of the same size, but filled completely with zeros. So we start with all zeros and we need to transform it into the target array. The only tool we have is a special operation. We can choose any continuous part of the array, a subarray, and increment all of its values by 1. Our job is to find the absolute minimum number of times we need to do this to get the job done. Okay, let's walk through an example to get a feel for it. Our target is 1, 2, 3, 2, 1. We start with all zeros. The first number in our target is a 1, so we definitely need at least one operation. A reasonable first move might be to increment the entire array. This gets us closer to all the target values at once. After one operation, our array is all ones. Now array is all ones. Looking at the target, the first element is already correct. But the second element needs to be a 2. So we need another operation that covers index 1. We could just increment index 1 by itself, but it's probably smarter to extend that operation to cover other elements we also need to increase, like the 3 and the other 2. So let's apply our second operation to the subarray, from index 1 to 3. Our array is now 1, 2, 2, 2, 1. We're getting closer. The only number that's still not matching is the 3 in the middle. So for our third and final operation, we just need to increment the element at index 2. And with that, we've successfully built the target array. In this case, it took us 3 operations. This matches the example, so it seems like a valid strategy. Okay, that manual walkthrough worked, but it feels a bit random. There has to be a more systematic way to think about this. Let's change our perspective. Instead of thinking about which subarrays to pick, let's think about what each element in the target array demands from us. The first element needs a certain number of operations. Then, when we look at the second element, how does its requirement relate to the first? Here's the core idea, and I think it makes everything click. Imagine the target array is a landscape, like a mountain range. We start at sea level, which is 0. The total number of operations we need is simply the total amount of uphill climbing we have to do. Let's trace it. To get from our starting 0 to the first value of 1, we have to climb up by 1. That's our first cost. Then, to get from 1 to 2, that's another climb of 1. And from 2 to 3 is 1 more. Now what happens when we go downhill? When we go from 3 down to 2, we don't need to start any new operations. Think about it. The 3 operations we used to build up that peak at index 2 are already covering the element next to it. Since that next element only needs to be a 2, those 3 operations are more than enough, so going downhill costs us nothing. The same logic applies when going from 2 down to 1, so the total cost is just the sum of all the uphill parts. 1 plus 1 plus 1 equals 3. This matches our answer. So this uphill climb idea gives us a very simple and powerful algorithm. The total number of operations will always be the value of the very first element. That's our initial climb from 0, plus any increases we see as we go from left to right through the array. If a number is bigger than the one before it, we add that difference to our total. If it's smaller or the same, we add nothing. That's it. Just a quick heads up. We'll be walking through the solution using Python. But don't worry if that's not your main language. I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. So let's formalize our approach, which we can call the uphill climb method. First, we'll set our initial answer to be the value of the very first element in the target array. Then, we'll loop through the rest of the array, starting from the second element. In each step of the loop, we just check if the current number is bigger than the one right before it. If it is, we add that positive difference to our running total. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through it line by line. And here it is. The Python code is incredibly short and clean, directly reflecting that simple logic we just discussed. Let's break down what's happening here. First, we create a variable, let's call it ans for answer, and we initialize it with the value of the first element of the target array. This accounts for the initial set of operations needed to raise the array from all zeros to the height of that first bar. Next, we start a loop that'll go through the rest of the array. We start at index 1, because we need to compare each element to the one that came just before it. Inside the loop is where the magic happens. We calculate the difference between the current element and the previous one. Then, we take the maximum of that difference and zero. This is a clever way to implement our uphill climb rule. If the current number is bigger, the difference is positive, and we add it to our answer. If the current number is smaller or equal, the difference is negative or zero, and the max function ensures we just add zero, effectively ignoring any downhill movement. So how efficient is this solution? For time complexity, we loop through the input array exactly once, so it's linear time, or big O of n, where n is the size of the target array. And for space complexity, we only use a single variable to keep track of our answer. No extra arrays or data structures are needed. That means it's constant space, or big O of 1. It's incredibly efficient. Alright, that covers the main solution in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. You can pause the video here to take a closer look at the implementation. Notice it's the exact same logic, just with Java syntax. Next up, here is the C++ version of the solution. Again, feel free to pause and review the code. The structure is identical to the others. And finally, here is the solution in JavaScript. Hopefully, seeing it in a few different languages helps solidify the concepts. So let's wrap it up. The biggest takeaway here is that a problem that seems complicated on the surface, involving subarrays and operations, can sometimes be solved by looking at it from a completely different angle. Instead of thinking about the operations, we thought about the requirements of each element. This led us to the simple uphill climb analogy, where only increases in value contribute to the final answer. Alright, before we jump into the other languages, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily LeetCode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads, and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more LeetCode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more LeetCode problems beyond the daily challenge, I've started a second channel called LeetCode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this LeetCode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.